Imagine a tool so powerful it can write stories, solve problems, even mimic human conversation. Large language models, like ChatGPT, are revolutionizing technology. But with that power comes risk. How do we keep them secure? How do we prevent misuse? Welcome to Business and Technology, where we break down the future of AI one deep dive at a time. Today we're tackling the top 10 risks and best practices for securing LLMs. From hidden vulnerabilities to cutting-edge defenses, we've got you covered. Let's get started. Okay, so when you're playing around with ChatGPT and you're kind of like, wow, this is pretty amazing. This feels like the future. Like these large language models, LLMs are powering so many tools now, it's just incredible.
Yeah,
But I feel like something people maybe don't think about as much as like all the work that goes into making sure that these things are safe and secure because they're so powerful.
huge amounts of power.
Exactly. And we're going to talk about all that today in this deep dive.
I'm excited for this one.
Yeah, me too. I mean, we've been talking about this topic a lot and reading all this stuff and
Yeah, just thinking about the future with all of this.
yeah, so we're going to delve into the security of LLMs. And I guess the first question is like, how do we even begin to think about this?
Well, I think it's important to start by recognizing that these LLMs we're talking about, systems trained on massive amounts of text data, like GPT-3, GPT 3.5, and these latest models like GPT-4, they're really revolutionizing the way we interact with technology. From content creation to customer service, even like medical diagnosis.
It really does feel like a fundamental shift.
It is. It's a paradigm shift. And with this immense power comes a huge responsibility to ensure their security, right?
Yeah, for sure. So that's the core question we're going to explore today, right?
Yeah. How do we protect these LLMs from potential attacks or misuse?
Exactly. And to do that, we've got a lot of really great material we're going to draw on from expert research industry insights, developer discussions, just to really unpack how these amazing technologies are being kept safe for everyone.
Yeah. And it's not just about like theoretical risks either.
Yeah,
They're real-world concerns.
absolutely. So let's kind of map out where we're going with this today.
Sounds good.
So we're going to look at the different defense strategies that are implemented throughout the life cycle of an LLM, from the very beginning when it's being trained all the way to when it's actually actively being used, to process requests and generate responses, which is what's called the inference phase.
Yeah.
So we'll begin by exploring how safety is built into these LLMs during their initial training.
Yeah. Like building it in from the ground up.
Exactly. And then we'll move on to discuss the safeguards that are active during inference.
When it's actually out there in the wild.
Exactly. And we'll also touch upon some of the top security risks identified by OWASP.
The Open Web Application Security Project.
That's right, for applications that are actually built using these LLMs, and we'll also talk about some of the best practices that are being used to mitigate those risks.
Sounds like a plan.
Okay, let's get started. So let's unpack this, starting with those defenses that are put in place during the training process.
Right. So building a secure LLM really starts at the very beginning, right? During that pre-training phase.
Yeah.
And that's when the model is first exposed to these huge datasets to teach it about language.
It's like its first taste of the world.
It is. And there are two main defense strategies that we see being used at this early stage.
Okay, so let's dive into those.
Okay, so first up, we have content filtering.
Okay, so that sounds pretty straightforward, like you're filtering out the bad stuff.
Exactly. It's all about identifying and removing harmful or toxic material from the training data before the model even starts to learn from it.
Makes sense.
And, we've seen this being applied in some of the most advanced models like Gemini 1.5 and Llama 3,
Right.
where they had these really strict safety guidelines applied right from the get-go.
I mean, intuitively it makes sense, right? If you start with cleaner data, you're less likely to have problems later on.
Absolutely. It's like,
But I imagine there's also a challenge here, like how do you define what's harmful?
yeah, that's the million-dollar question, right?
Yeah,
It's subjective, and it can vary a lot depending on the context.
right.
So different models and applications might have different thresholds, and those filtering mechanisms themselves, they can sometimes be a bit too broad or too narrow.
Yeah, I could see that, like sometimes maybe missing some harmful stuff or sometimes being too strict and over-censoring things that are actually fine.
Exactly. And to address that, teams often employ a whole range of techniques, from simple keyword lists to machine learning classifiers that can learn to recognize patterns of harmful language.
Right?
And in some cases, yeah, they even have human review to double check and make sure that the filtering process is working as intended.
Yeah, because sometimes you just need that human judgment to make those nuanced calls.
Absolutely.
Okay, so that's content filtering, kind of like cleaning up the data before it even gets fed to the model.
Right? And the second pre-training defense we see is conditional pre-training.
Okay, this one sounds a little more complex.
Yeah, it is a bit more nuanced. So instead of removing the potential...
Okay, so it's like flagging it somehow.
Exactly. So as the model learns from this data, it also learns to associate these markers with undesirable outputs or contexts where it needs to be extra careful.
So it's like giving the model a heads up.
Yeah, like a little warning sign saying, hey, handle this with care.
I see.
And Paul M2 is one example of a model that uses this technique.
Okay, so you're not getting rid of the data entirely, but you're sort of giving the model some context about it.
Precisely.
Okay, so those are the pre-training defenses, like the first line of defense.
Right? Like building in those safety measures from the ground up.
Now, what happens after the model has gone through that initial learning phase?
Well, that's where the post-training defenses come in.
Okay, so now we're talking about refining the model's safety even further.
Exactly. And one of the most widely used techniques here is supervised fine-tuning, or SFT.
SFT, so it sounds like we're getting very specific with the guidance we're giving the model here.
We are. Yeah? So, with SFT in the context of safety, we're essentially showing the model examples of inputs that are considered unsafe,
Okay,
and crucially demonstrating the desired response, which is to refuse to engage with or answer those harmful requests.
right.
So, like giving it specific training on how to say no.
And does that actually work? Like, can you really teach these models to just refuse to answer certain types of questions?
It's actually quite effective. Yeah,
Really?
absolutely. Yeah. There's been some research that's shown that even using a relatively small amount of this, what they call rejection-specific data, like around 3%, can have a noticeable impact on how well the model handles harmful prompts.
Wow, 3%, that's pretty impressive.
It is. But the key here is to make sure that you're providing the model with a really diverse range of examples.
Right.
Covering all sorts of different types of unsafe scenarios so it learns to generalize.
You don't want it to be like, oh, I only recognize this one specific type of harmful prompt, and then anything else, it's like, oh, okay, sure, I'll answer that.
Exactly. It needs to be prepared for a whole spectrum of potential issues.
Right? Okay, so that's SFT, and what's the next tool in our post-training safety toolkit?
So another really powerful technique is adversarial training.
Okay, adversarial training. That sounds kind of intense.
It can be. Yeah, it's like a constant challenge for the model.
A challenge? How so?
So imagine this. You have one AI system that's specifically designed to generate challenging, potentially unsafe input examples.
Okay.
And then you have the LLM that we're trying to make safer. And it's being trained to recognize and reject these deliberately tricky inputs.
So it's like an AI versus AI battle.
Exactly. It's like having this internal red team within the AI system itself constantly probing for vulnerabilities and pushing the main model to become more resilient.
So the one AI is trying to trick the other AI, and the other AI is trying to not be tricked.
Yeah, exactly. And then to guide this whole process, they often use what are called reward models.
Reward models.
Yeah. So these help the system to distinguish between helpful responses and unsafe responses.
So it's like a scoring system.
Exactly. It learns to recognize what a good response looks like and what a bad response looks like.
That's really interesting, using AI to fight AI in the name of safety.
It's a really cool concept, right?
It is. Now, we also saw mention of layered safety measures. What does that mean exactly?
So that's the idea that you don't just rely on one single defense mechanism,
Right.
especially with complex systems like LLMs. You want to have multiple layers of protection to create a much more robust and resilient system.
Yeah, like a multi-pronged approach.
Exactly. And one example of this is two-step safety fine-tuning.
Okay, 2 steps, so walk me through that.
Okay. So in this approach, the model first learns to analyze an incoming question or prompt
Okay,
and determine if it has the potential to be harmful.
so it's like an initial screening.
Exactly. And then in the second step, it evaluates the safety of the specific answer that it's about to generate.
So it's double-checking itself.
Yeah, it's like having a built-in safety net.
That makes sense. And we also came across something called adversarial optimization.
Yes. So this is where things get really sophisticated.
Oh boy.
It involves using these specialized algorithms to really push the model to its limits and strengthen its resistance to even the most difficult or cleverly designed malicious inputs.
So it's like taking that adversarial training to the next level.
It is. It's like putting the model through boot camp.
Wow. So is this something that everyone does, or is it more for the really advanced teams?
It can be quite computationally expensive.
Yeah.
It requires a lot of resources. So for teams that maybe have more limited resources, there are simpler but still effective alternatives, like soft prompt tuning and low-rank adaptation or low-ray.
Okay, so there are options depending on what you have available.
Yeah, you can still enhance the model's safety without having to do a full retraining.
That's good to know. Now, one term that you hear a lot in these discussions about LLM safety is RLHF reinforcement, learning from human feedback.
Yes, RLHF. That's become a really central concept.
It seems like it's kind of everywhere now.
It is. And for good reason. It's been really effective.
So tell me more about how it actually works.
So the basic idea is to train a separate reward model based on feedback from humans.
Okay.
So imagine this: human reviewers are presented with different possible responses to the same prompt.
Okay.
And they rank these responses according to various criteria, like how helpful it is, how accurate it is, and importantly, how safe it is. And the reward model learns to predict which kinds of responses humans prefer.
So it's like teaching the AI what we consider good behavior.
Exactly. And then this prediction is used to guide the fine-tuning of the main language model.
Constitutions.
Precisely. And one of the cool things about RLHF is that it's been particularly effective at improving how the model handles complex or ambiguous situations.
Right. Because those are the situations where it's really hard to pre-program all the rules.
Exactly. You need a more nuanced approach, and RLHF seems to provide that.
But I imagine there are also some challenges with this approach.
There are. Yeah. One of the biggest challenges is creating those high-quality preference datasets.
That's the data used to train the reward model, right?
Exactly. And to make those datasets, you need a lot of human annotations, which can be time-consuming and expensive.
Right.
But researchers are working on this. There are efforts to develop more efficient ways to collect and annotate this data.
So trying to make that feedback process more scalable?
Exactly. And there's also some really cool research on using what are called reverse instruction models.
Reverse instruction models. Okay, this is a new one.
Yeah. So these models are trained to kind of do the opposite of what a regular language model does.
Okay.
Instead of taking a prompt and generating a response, they take a desired response.
Right.
And then try to generate a prompt that would naturally lead to that kind of response.
So it's like working backwards.
Exactly. And you can use this to automatically create new tasks and prompts from existing safe content.
Interesting. So you're basically leveraging the model itself to help you generate more training data.
Yeah, pretty neat, huh?
It is. Now, what about RLIF reinforcement learning with AI feedback?
Ah yes, RLEF. This is a really interesting development.
It sounds similar to RLHF, but with a key difference.
Right? So with RLHF, you're relying primarily on human feedback to train that reward model.
Right.
But with RLAEF, the feedback is actually generated by another AI system.
Okay, so the AI is evaluating itself?
In a way, yes. And this AI feedback is guided by a set of predefined safety rules or principles, often referred to as constitutions. Yeah, it's like giving the AI its own internal moral compass.
I see. And so the idea is that this can reduce the reliance on having these huge teams of human annotators.
Exactly. It can make the process much more scalable. And systems like Claude and Quentu have reportedly made really effective use of this RLAF technique.
So it's still early days, but it seems very promising.
It does. Yeah, it's definitely an area to watch.
Okay, so now we've talked about how we get this feedback from humans or even from other AI systems, but how do we actually use this feedback to change the LLM's behavior?
Right? So that's where preference optimization algorithms come into play.
Okay, so now we're talking about the actual mechanics of tweaking the model.
We are. And one of the most
PPO.
yeah. And it was famously used by OpenAI in their Instruct GPT model. So what PPO does is it dynamically adjusts the model's outputs based on the scores it gets from that reward model.
So it's like a continuous feedback loop.
It is. And it's proven to be very effective, but it can also be quite computationally expensive.
Right.
But there are some more memory-efficient variations of PPO that have been developed as well.
So there are always trade-offs.
Always.
Yeah, okay. And what about direct preference optimization, or DPO?
So DPO takes a bit more of a direct approach.
Okay, how so?
So instead of training a separate reward model and using reinforcement learning,
Right.
DPO directly adjusts the main language model's parameters using the collected preference data.
Okay, so it's more straightforward.
Yeah, it's simpler, and it's been adopted in models like Zephyr and Llama 3.
Okay.
But because the feedback isn't as specifically tailored to the nuances of the model's responses,
Right.
it might not generalize as well as PPO in really complex situations.
I see, so it's simpler but maybe not as powerful. And then we also saw this ongoing challenge of balancing helpfulness and harmlessness,
Yeah, that's a really tricky one.
because you want the model to be useful, but you also don't want it to be dangerous.
Exactly, and sometimes those two goals can be in tension.
Yeah, I can see that happening. Like, if you're too strict with the safety constraints, it might prevent the model from giving you useful information.
Exactly. Or it might make the responses really bland and generic.
Right, so it's a delicate balance.
It really is.
Okay, now shifting gears a little bit, we came across the term representation engineering.
Yes, representation engineering.
Yeah,
This is getting down into the nitty-gritty of how these models work.
it does feel like we're going a level deeper here.
We are. So instead of just focusing on tweaking the inputs or the final outputs of the model,
Right.
representation engineering is all about trying to understand and directly manipulate the internal representations of knowledge and language that the model has learned.
Okay, so can you break that down for me a little bit? Like, what does that actually look like in practice?
Sure. So imagine that the LLM has its own internal map of knowledge and language, and representation engineering is about trying to understand and maybe even redraw parts of that map.
So we're getting into the model's brain.
We are. Yeah. And there's some really cool techniques for doing this, like knowledge editing, which allows you to make very specific changes to certain layers or components within the model.
So you can actually go in and, like, change the model's knowledge.
Yeah. Like, you could add new factual information or remove undesirable knowledge that it might have picked up during training.
Wow, that's pretty powerful.
It is. And then there are also what are called steering methods.
Steering methods.
Yeah. So these involve analyzing those internal representations to really understand how the model processes information and makes decisions.
So it's like observing the model's thought process.
Exactly. And all of this can be used to improve safety.
Okay, how so?
Well, for example, by figuring out which internal representations are associated with generating harmful outputs, you can then try to steer the model away from those states.
So it's like redirecting its attention?
Exactly. Towards representations that are linked to safe and appropriate responses.
That's really fascinating. So it's like building safety into the core of how the model thinks.
It is. And there's even some research on developing what they're calling circuit breakers. Circuit breaker.
Circuit breaker.
Yeah. Like actual mechanisms within the model that can directly interrupt the generation of harmful content based on these internal representations.
Okay, so it's like a safety switch that can just shut things down if they're going in the wrong direction.
Exactly. It's a really interesting area of research.
Okay, so we've covered a lot of ground here about how we can defend these models during training.
A lot of different techniques.
Right, but now let's move on to the next critical stage, which is defending LLMs during inference when they're actually out there being used to respond to our prompts.
Right. So once an LLM has been trained and deployed, it's generally not a good idea to keep retraining it every time you need to make a change.
Yeah, that would be pretty inefficient.
So we need different techniques to ensure safety during inference.
Okay, so what are some of the key approaches here?
Well, one really important area is prompting,
Prompting. That's how we communicate with the LLM.
right? Exactly. It's how we give it instructions and ask it questions.
So how can the way we formulate our prompts contribute to safety?
There are several effective prompting strategies. One is prompt rewriting, which is where you take the user's initial input and you subtly adjust it or rephrase it to encourage the model to generate safer responses.
So it's like nudging the model in the right direction.
Exactly. And for example, you might add phrases that explicitly emphasize responsible use
Right.
or avoiding harmful content,
So you're being very explicit with your instructions.
right? And there are even automated techniques like reducing potential offense or RPO.
RPO.
Yeah, which analyses prompts to identify and modify suffixes that tend to lead to less harmful outputs.
Okay, so it's like a safety filter for your prompts.
It is. And then there's another really interesting approach called self-reflection prompting.
Self-reflection prompting. That sounds pretty meta.
It is. So the model is actually instructed to generate a response and then review its own output for potential safety issues before showing it to the user.
So it's like double-checking its own work.
Exactly. It's like giving it a conscience.
That's pretty amazing. Okay, and then we have few-shot prompting.
Ah, yes, few-shot prompting. This is where you provide the model with a few examples of safe and appropriate behavior directly in the prompt itself.
Okay, so you're giving it some good examples to learn from.
Exactly. And this can be particularly helpful in steering the model away from adversarial or potentially harmful requests.
So it's like setting a good example.
T is. And sometimes this is combined with retrieving relevant safety-related examples from a knowledge base and including those in the prompt as well.
So you're really reinforcing that desired behavior.
Right.
Okay, and we also heard about chain of thought prompting in the context of safety.
Yes. So chain of thought prompting encourages the model to break down complex queries into a series of logical steps. So instead of just jumping straight to an answer, it kind of walks through the reasoning process step by step.
So it's thinking out loud.
Yeah, in a way. And this can really help the model to apply those safety rules more effectively.
I see. So it's not just about the final answer. It's about how it gets there.
Exactly. And that can lead to safer, more considerate responses.
Okay, so it seems like prompting techniques offer a lot of flexibility because you don't have to retrain the entire model.
That's right.
But are there any drawbacks or limitations to this approach?
There are. Yeah. I mean, using really long prompts with lots of examples or complex reasoning chains that can increase the computational resources required, and it can potentially slow down the model's response time.
Right, I can see that.
And there's also a subtle risk that if the examples you provide inadvertently contain unsafe content, then that could actually influence the model's behavior in a negative way.
It's like teaching it the wrong lesson.
Exactly. So prompting is often most effective when it's used in combination with other defense mechanisms.
So it's not a silver bullet, but it's an important part of the overall strategy.
Precisely.
Okay, so now let's talk about guardrail systems.
Ah, yes, guardrails. These are like dedicated safety filters that sit around the LLM.
Okay, so they're like a protective barrier.
Exactly. And they carefully examine both the inputs that are sent to the LLM and the outputs that it generates.
So they're checking things on both ends.
Right. And they can include all sorts of components like prompt filters to block harmful requests, toxicity detectors to flag inappropriate language,
Okay,
and even mechanisms to guide the model towards more ethical and responsible responses.
so they're really trying to keep the model on the straight and narrow.
They are. And there are some really sophisticated guardrail systems out there.
Are there? Like, what are some examples?
Yeah. So Nemo Guardrails is one example.
Okay,
And it actually uses LLMs themselves along with structured databases and the specific language called Golang.
Golang.
Yeah, it's pretty cool. They use it to define and enforce these safety rules.
So it's AI protecting AI.
It is. And then there are also tools like SPML, which is specifically designed to help developers create secure prompts from the very beginning.
Okay, so it's like baking security into the design process.
Exactly. And sometimes these guardrail systems even employ fine-tuned machine learning models
Right?
that are specifically trained to double-check the safety of the prompts and the responses.
So it's like having a dedicated security team for your LLM.
Yeah, right?
That's really impressive. Okay, now another interesting approach we saw was language model ensembling.
Ah, yes, ensembling. So this is where you combine the outputs from multiple different LLMs.
Okay, so it's like a team effort.
It is. The idea is that by aggregating and analyzing the predictions from several distinct models,
Right.
you can reduce the risk of any single model producing an unsafe or inaccurate output.
So it's like a checks and balances system.
Exactly. And one example of this is moving target defense, which involves combining responses from multiple commercially available LLMs and then strategically selecting the one that's deemed to be the most helpful and the least harmful, which involves combining responses from multiple commercially available LLMs and then strategically selecting the one that's deemed to be the most helpful and the least harmful.
So it's like a voting system?
Yeah, kind of. But this approach can be quite computationally demanding,
Right.
and it might introduce some latency in the response time.
So it's a trade-off.
Yeah, always trade-off.
But it sounds like it could be really valuable for situations where you need a very high level of reliability.
Absolutely, like in healthcare or finance,
Right.
where the stakes are really high.
And we also saw a more complex debate-based approach.
Yeah. So this is where multiple models actually discuss a sensitive topic among themselves.
Okay, this is getting really interesting.
Yeah. They present different viewpoints and refine their answers through rounds of interaction.
So it's like a panel discussion, but with AIs.
Exactly. And this can be really effective at improving safety, especially when you're involving smaller, more specialized models with different safety biases.
But I imagine this is even more computationally expensive.
It is. Yeah. So ensembling is a powerful technique, but it's often reserved for applications where that extra layer of security is really critical.
Okay, so it's like the heavy artillery of LLM safety.
You could say that.
Okay, now in the realm of inference time defenses, we also have techniques to address adversarial suffixes. What exactly are those?
Right? So these are kind of sneaky.
Oh boy.
They're small pieces of text that are very carefully crafted to trick the language model.
Okay.
And they're added to otherwise harmless prompts with the intention of getting the model to generate harmful or inappropriate or just unexpected content.
So it's like a hidden trap.
It is. And because the main part of the prompt might look completely innocent, these adversarial
Right.
suffixes can often bypass those standard keyword-based filters.
So they're designed to be stealthy.
Exactly.
So how do we go about detecting and neutralizing these things?
Well, one method is called perplexity filtering.
Okay, perplexity filtering.
Yeah, so perplexity is a measure of how unusual or unexpected a sequence of words is.
Okay.
And a suffix that results in a really high perplexity score.
Right.
That might be a sign that it's an adversarial attempt.
So it's like it sticks out like a sore thumb.
Exactly. But the challenge with this method is that it can sometimes flag legitimate prompts as harmful.
Right, so you get false positives.
Exactly. So to try and improve the accuracy, they often use machine learning classifiers,
Okay.
like light GBM, which are trained to distinguish between genuine text and those malicious suffixes based on various linguistic features.
So you're using machine learning to try and spot those patterns.
Exactly.
Okay, and then we also came across perturbation-based methods. What are those all about?
So these methods exploit the fact that adversarial suffixes are often very sensitive to even small changes in the surrounding text.
Okay.
So one technique is called the erase and check algorithm.
Erase and check.
Yeah, it's pretty straightforward. It works by systematically removing words from the end of the prompt one at a time,
Okay.
and then checking if the remaining shorter prompt is still flagged as harmful.
So you're kind of stripping it down to see if the core problem is still there.
Exactly. And if any of those truncated versions of the prompt are flagged as unsafe, then the whole original prompt, including the suffix, is considered malicious.
That's a clever approach. And then there's also randomized smoothing.
Yes, sometimes called smooth LLM.
Smooth LLM.
Yeah, this one's cool. It involves adding these small random variations to the input text,
Okay.
like inserting, deleting, or substituting words with similar meanings.
So you're introducing a bit of noise.
Exactly. And this can actually disrupt those carefully crafted adversarial suffixes and make them less effective.
So you're kind of throwing a wrench in the works?
Yeah, pretty much.
Okay, so we've covered a lot of ground here on the various ways that we defend these LLMs.
It's a whole arsenal of techniques.
Right, but now let's shift our focus to the specific risks that these systems face.
Okay?
And we saw that OWASP, the Open Web Application Security Project.
Right. A very well-respected organization in the security community.
Exactly. They've actually put together a top 10 list specifically for LLM applications.
Yeah, they have. And it's really helpful for understanding the key security risks that are unique to systems built using these large language models.
So let's walk through those top 10 risks.
All right. So number 1 is prompt injection.
Okay, we've talked about this quite a bit already, right?
We have. Yeah. It's the risk of malicious actors manipulating those prompts to get the LLM to generate harmful or unintended responses.
So it's a very real threat.
It is. And to mitigate this, you need really robust input validation and sanitization to identify and neutralize those potentially harmful components of the prompt. Exactly. And you also want to have anomaly detection systems in place to spot any unusual patterns in user inputs that might indicate an attack.
So you're looking for anything that's out of the ordinary.
Right.
Okay, number 2 is insecure output handling.
Right. So even if the initial input is safe, the LLM could still generate something harmful or sensitive or inappropriate in its output.
So it's like you have to be careful on both ends?
Exactly. And to mitigate this, you need robust output filtering and validation
Right.
to catch any problematic content before it gets released.
So you're basically scrutinizing the model's responses.
You are. And it's also really important to have clear policies in place about what types of information the LLM should and should not generate.
Right. So you're setting boundaries.
Exactly. And of course, you need continuous monitoring of the outputs to make sure that nothing slips through the cracks.
Okay, makes sense. Now, number 3 is training data poisoning.
Right. This is a big one.
So this is where attackers try to tamper with the data that the model learns from.
Exactly. They try to sneak in malicious data that can corrupt the model's behavior.
And how do you protect against that?
Well, first of all, you need to make sure that you're using verified and secure sources for all your training data. Exactly. And then during the training process itself, you want to have anomaly detection mechanisms in place to spot any unusual patterns or data points that might indicate a poisoning attempt.
So you're looking for anything that's out of place.
Right. And then even after training, you need to continuously monitor the model's performance to make sure that its behavior hasn't been compromised.
So it's like ongoing vigilance.
It is.
Okay, number 4 is model denial of service.
Right. So this is where attackers try to overwhelm the LLM with a flood of requests.
Okay, so they're trying to make it unavailable to legitimate users.
Exactly. They're trying to take it down.
And how do you protect against that?
Well, a lot of the standard denial of service mitigation techniques apply here,
Okay, like what?
like rate limiting,
Okay,
which restricts the number of requests from a single source within a given time frame.
so you're preventing any one user from hogging all the resources.
Exactly. And then strong authentication
Yay.
to make sure that only authorized users can access the model.